Okay, today we're going to be talking about double displacement reactions. And if you'd like to follow along, I'm going to be doing some of the examples on page 17 in your packet. I'll do the first few up there, and the ones in the middle there you can try on your own, and I'm going to do one of the ones down at the bottom as well. So, to start off here, in a double displacement reaction, we're going to have two compounds. So, we're going to have a compound. We'll add that to another compound. And if we have a reaction, we are going to end up with two different compounds than we had before. So we'll get another compound and a compound as our product here. And we'll see how it happens in a little bit, but you may not always have a reaction take place. Let's just look at a few examples so that we can see how that will work out. So let's just look at the first example on page 17 there. So let's say we have mercury chloride. And we're going to see if that reacts with lead sulfate. So this type of reaction is going to be where it's really important to keep track of your physical descriptors. So what state your compound is in. Is it aqueous? Is it solid? Is it liquid? Is it a gas? This is where it's going to be important, at least for our products. As our reactants, we usually will just assume that our reactants are in an aqueous solution because that's how we can get the interaction of ions that we are going to want to look at. So both of our reactants will start out as aqueous, and then as products, then we're going to have to keep track of how that happens. Now, in an aqueous solution, as you know, that's going to be when our salts dissociate into their ions that make them up. So in this solution here that we currently have, we have mercury chloride and we have lead sulfate, and what that's actually going to look like then is mercury ions and chloride anions and lead ions and sulfate anions. So this is going to be what's actually in our solution here because we have two salts that have dissociated, and as we dissociate the salts, we get these things out because they're going to separate out and we get those. What we're going to do then is see if they can react with something that they were not with before. So we're going to take this mercury here, and it used to be paired up with the chlorine, so we're going to pair it up with the other anion. Cations can go with anions, and so we can just take this, see if it will pair up with what it was not with before, and likewise this lead was with sulfate before, so it can go with something different. We'll see if it goes with the chlorine. So the outer ones go with the outer ones go with the outer ones, and the inner ones go with the inner ones, and we'll see if they react. So let's take our mercury and see if it goes with the sulfate. So at this point we just put it together and make a compound like we always have. So since this mercury has a +1 charge and the sulfate has a -2 charge, they're going to go together in an appropriate compound. So we get mercury, and we will need 2 of those to balance out 1 sulfate. And we are going to have, for our other compound then, lead. And remember, when you're writing compounds, the cation always goes first. Even though our chlorine is listed first here, we always put the positive one first. So we get lead chloride. And on this one, we need 2 of the chlorides to cancel out with the lead. We had our initial reactants up here. This was a reactant. This was a reactant. And we get our products at the end. But, and this is where we have to keep track of our physical descriptors, this reaction may not have actually taken place. How we can tell is we can look at this periodic table, and we'll use our solubility chart, and let's look to see what we have for products. Our first one here, we had mercury and sulfate, so we'll go through on our solubility chart, and we find mercury, and this happens to be mercury 1 in this case, so mercury 1, and sulfate, and that is a solid. And lead to chloride, look here for lead 2 and chloride. That is going to be partially soluble. So we'll put PS there. Now, the reason why this is important, in this case the reaction did work out because we ended up with something that's different than what we started with, but just hypothetically, if this had not been a solid here, let's say that had been aqueous, and this had also been aqueous, what would we have ended up with? Well, if both of these had been aqueous, we would have actually had mercury ions, and sulfate ions, and chloride ions, and lead ions. Nothing would have actually changed. So if you don't have some type of change of state for something in the solution, you did not have a reaction. In order to have a reaction, you must have a solid, liquid, or gas come out of solution. In our real reaction here, these weren't aqueous. This had been a solid, and partially solid does work on that, or partially soluble, because that means you would have a little bit of precipitate come out, so that is sufficient to count as being one of our things that was coming out of our solution. But we have to have something come out of solution, or this didn't actually happen. We wouldn't have had any evidences of a chemical change. We would have started with a solution with various electrolytes in it, and we would have ended with a solution with various electrolytes in it. So to have a reaction, we must have some type of different physical descriptor at the end. So let's try another one. This time we have hydrogen nitrate reacting with silver iodide. Again, when we look at this, we're going to put a cation with a different anion than it had before. So our hydrogen is going to go with the iodide, and our anion is going to go with the opposite cation. So our nitrate is going to go with the silver. So our products, and we can write them in either order, it doesn't matter which one you put first, but we have hydrogen iodide and silver nitrate. Now we also need to look at our charges at this point. Hydrogen is +1, iodide is -1, so that works. And then we have silver is 1 from, we can see the reaction there, that could have been variable, but it happened to be 1 in this case. And our nitrate also, if we look on our polyatomic list, is a -1. So we do have our compounds there. But at this point we need to look up and see if we actually had something happen. So for first our hydrogen iodide, so we look up here, we find hydrogen, we go over to iodide, and that is aqueous. Then we do the same thing with our silver and our nitrate. So we have silver, we go over to nitrate, and that is aqueous as well. Since we started out with 4 ions in solution, and we ended with 4 ions in solution, nothing changes with this potential reaction. So that means that there's no reaction to have actually happened. So what we would do at this point, just write a line through this and put no reaction. So if there had been a reaction, these would have been our products, but since they are both aqueous, nothing actually happened, so the correct answer to this would have been no reaction. And if you put these as actual products, that would have been incorrect because there's nothing that truly took place here. Let's try another one. So this time we have hydrochloric acid, and we're going to react it with iron 2 hydroxide. So our hydrogen is going to go with the hydroxide, and our iron is going to go with our chlorine. And remember, this is iron 2 because we needed 2 of these -1s to cancel it out, so that's how we know what the charge on that iron is going to be. So we now need 2 chlorines to go with it as well. So if you notice at this point, the formula for this is actually H2O. And we know that H2O is not an aqueous solution, it is a true liquid. Water isn't just dissolved in itself, it's actually a molecule. So this is a liquid then, and at this point we know that this is a true reaction. And over here, we can look this up. It's not really going to matter at this point what its state is as far as determining if a reaction happened. But if we look through iron to chloride, it is aqueous. But because this water over here, our HOH, our dihydrogen monoxide, is a molecule, it's a liquid, that is going to be sufficient for us to be able to say that this reaction happens. So these are our two products. We had our reactants, hydrochloric acid, iron 2 hydroxide, and we ended up with liquid water and aqueous iron chloride. There's just one more thing to mention down at the bottom of page 17 there, where it says acid-base reactions are a special double displacement reaction. So acid-base is a type of reaction that there is, and that's just where we have an acid. So for instance, hydrochloric acid, we can get that off the back of our periodic table, and a base is anything that has the hydroxide anion, so plus sodium hydroxide. We're always going to get two things out of that. We're going to get water plus a salt. So due to the fact that we're getting water out of this, this is always going to take place because water is a liquid, so that gives us our true product that we're going to get out of the reaction. Now let's see what our salt is here. So when we switch our cations and anions, we have hydrogen and hydroxide, so that gives us the HOH again, our H2O, our water, that's going to be a liquid. And we have sodium chloride left over, are the two other ions that we had. So we're going to get water and sodium chloride, and if you look this up, this is going to be aqueous as well. So this is a acid-base reaction. It's the exact same thing as a normal double displacement. We just know what the products are going to be ahead of time. It's going to be water and some type of salt. But if you don't have that memorized, that's fine. You just go about it the same as you would in the other one and recognize that HOH, that is water, it is a liquid. I haven't mentioned it up to this point, but at the end of any of these, if you do have a reaction, you would need to go back and balance what you ended up with. So you end up with products, you had reactants, those have to be balanced so that you have the same number of atoms on both sides, because when you have differing charges, you may end up with different amounts of atoms, so you'll have to balance that with your coefficients, but that's not going to actually affect the reaction itself on whether it proceeds. So first, see if the reaction proceeds. If it does not, if it's no reaction, you can stop there. If it does, you will need to go further and balance it at that point. So do the ones on page 17 that we did not balance, and then the rest of your assignment will be to go on and do page 20, the rest of it that you have not done before, all the double displacement reactions now. And again, the overall process, look at the two compounds you have, separate it all out into ions, and at that point it may be helpful to write out the ionic charges above everything. So write the charge of the cation, the charge of the anion, so that you can keep track of those. If you aren't doing that in your head, that's fine. And then put the cation with the opposite anion, put the other anion with the opposite cation, see if you will get something besides an aqueous solution out of it, and if so, you have a reaction and you need to go and balance it.